The Unknown Universe. Nature of Space-Time. By Kishockkanthan Sivapragasam. Purpose of this presentation. My name is Kishockkanthan Sivapragasam, Kishok. I have always wondered about the grand design of the universe, and had great curiosity, knowledge, and highly devoted to understanding how things in the universe work. I feel I am born with the knowledge of science and have a great passion to disclose the universe's long-standing secrets which may take the science world to the next level. I believe that nature is written in a language that anyone who's devoted to understanding the language can understand. I have done some significant thought experiments in regard to the concept of space-time for nearly the last 10 years. I started my thought experiments originally basing on motion effects which dealt with great implications even beyond Lorentz transformation, from which Einstein's theory of relativity derived. Having developed my own thought experiment for years, I came across to understand at some point that most of the aspects of the result of my experiment were proposed and became as laws of physics during the last centuries. Therefore, I have explained some of the experiments in my presentation relating to the result of the theories. I decided to explain something remarkable about space-time. There had already been a great number of studies about the universe, however, I felt that none of them really addressed the questions in the way I look at the universe, hence the presentation. The purpose of my presentation is to provide a new perspective of understanding space-time, that would explain how the measurement of space and time depend not only on how fast a body is traveling but also on directions in which it is traveling, and answer to one of the most significant questions of why time flows only in the single predetermined direction, toward the future. Special theory of relativity, Hubble's discovery and Big Bang. In 1905, Albert Einstein published the theory of special relativity, which told us something amazing, that we were completely wrong about the way the universe works. Einstein replaced the laws of Newton and Galileo with his theory of special relativity, which showed how space and time are really related. Special relativity shows that measurements of distance and time depend on how fast you are traveling. In the late 1920s, the American astronomer Edwin Hubble made a very interesting and important discovery. Hubble made observations that he interpreted as showing that distant stars and galaxies are receding from Earth in every direction. Moreover, the velocities of recession increase in proportion with distance, a discovery that has been confirmed by numerous and repeated measurements since Hubble's time. The implication of these findings is that the universe is expanding. Hubble's hypothesis of an expanding universe leads to certain deductions. One is that the universe was more condensed at a previous time. From this deduction came the suggestion that all the currently observed matter and energy in the universe were initially condensed in a very small and infinitely hot mass. A huge explosion, known as the Big Bang, then sent matter and energy expanding in all directions. Note: Einstein's special theory of relativity was proposed more than 2 decades before Hubble discovered that the universe was expanding. While it is true that the model Einstein proposed at that time, in which the universe is static, he added a term to his equations which he called the cosmological term, and said that would produce a small repulsive force throughout all of space that would hold the universe together. Motion effect in directions. This thought experiment is designed to explain how one's measurement of distance varies depending on the directions in which a body is traveling relative to something else, example, Earth. Imagine that you are traveling within the gravitational field, either by air or on land, at the same speed and in the same direction as Earth rotates to east. In this case, you will be moving 2 times faster than the speed of Earth when observed from outside the gravitational field. This means that you covered twice the distance that is covered by Earth at a specific time. This would result in 2 sunrises in 24 hours. On the other hand, If you travel at the same speed as Earth in the opposite direction to the rotation of Earth to west, you will be standing still in a suspended position in space or on Earth and will not have any movements around the Earth except the Earth that revolves around the Sun. Imagining the event that's taking place on a train that is in motion would be easier to understand and further this experiment. Motion effect on a moving train. As illustrated in picture 1 above, imagine a train with two runners A and B on either side of the train, both at exactly the same distance from point X, and an observer I is standing on the ground at Earth position K. The train is in motion at a constant speed on a straight line toward east, and A and B are running at the same speed as the train, to the point X. The train is traveling on a straight line toward east at a constant speed. J, K and L are Earth lines. A is running to point X eastward at the same speed as the train. B is running to point X westward at the same speed as the train. X is the midpoint of A and B. I, an observer, remains stationary on the platform on Earth line K and observes the event. Which runner would reach the point X first, A or B? Measurement of speed and distance. From the perspective of the observer I, A's speed is twice the train and covers twice the distance that the train covers at a given time. B appears to be remaining at the same point relative to Earth. Although B is running toward the point X, he remains at the same Earth line L. In fact, it is the point X that is moving toward B. When the point X on train reaches the Earth position L, the positions of A, B, and X will be as illustrated as shown in the animation below. The both runners will have reached the point X simultaneously. A will have reached the train point X, and at the same time the Earth point L. B will have reached the train point X, and remained in the same Earth point L. This simple experiment is fundamental to the discussion of the presentation. Motion effect on a moving train, animation as follows. Michelson and Edward Morley's experiment. In 1887, two American scientists, Michelson and Edward Morley, carried out a very sensitive experiment designed to measure the speed at which the Earth travels through ether. Their idea was to compare the speed of light in two different directions. If the speed of light is a fixed number relative to the ether, the measurements should have revealed that the light speed differed depending on the direction of the beam. But Michelson and Morley observed no such difference. As a result, they began to accept the idea that the speed of light is the same in all directions. Based on the Michelson-Morley experiment, the Irish physicist George Fitzgerald and Dutch physicist Hendrik Lorentz suggested that bodies moving through ether would contract and that clocks would slow down. This construction and slowing down of clocks would be such that people would all measure the same speed for light, no matter how they were moving with respect to the ether. The discovery that the speed of light appeared the same to all observers, no matter how fast and in which direction one was moving, let Einstein derive the theory of relativity. Einstein began his theory of special relativity with two assumptions. 1. The laws of physics are the same wherever you are. This means that an experiment carried out in a moving train will give the same results as when it is performed in a lab. 2. The speed of light is the same for everyone. What Einstein then stated was that in order for all observers to measure the same velocity for a beam of light, time would have to flow differently for different observers, and space would sometimes have to contract. The special theory of relativity states that regardless of the direction in which a body is traveling, the faster a body travels closer to the speed of light, the slower the time flows relative to someone at rest or traveling slower. Measurement of space-time. According to my understanding regarding motion of bodies, the measurement of space and time depend on the direction of motion of bodies relative to the observer. The faster a body is traveling in the same direction as the expansion of space, the slower it experiences time relative to someone who's traveling slower or traveling in the opposite direction to the space expanding direction or being at the absolute rest. The following experiment may explore the implication clearer. Imagine the same train experiment with identical clocks at each point A, B, X and I. Time on each clock is synchronized with respect to each other when the train is standing still at the platform. This experiment is designed to understand how the same events that take place in different directions on a moving train would distinguish the measurement of time. Imagine, as in the above example, the train is moving at a constant speed, having a clock fixed at point X in the center of the train being approached by two runners A and B at either end, both at exactly the same distance from the point X. According to the special theory of relativity, the two runners should measure time ticking exactly the same since they are at exactly the same distance from the center point X, moving toward each other on a straight line at the same speed as the train. What about the observer's measurement in relation to A, B and X when the train is in motion in a predetermined direction, toward east? While the train is in motion at a constant speed toward east, displacement and time dilation takes place. The changes that take place when runners have reached the point X are illustrated in picture 2. Measurements of time. From the perspective of the runners and point X on the train. According to the special theory of relativity, A, B and clock at point X should show the same time when the runners have reached the point X. Since both the runners have covered the same distance at the same given time, hence the speed is the same. However, it'll be explained further later in this presentation. From the perspective of the observer I, B remains at the same exact earth point L while the point X reaches the runner B, therefore time on B's clock will agree with the time that the observer measures on his own clock. In other words, B is at rest with respect to the observer I. The clock at point X is moving in the same direction as the train, while B remains in the same position. The time measured on the clock at the point X will show a time less than the time that has ticked on B's clock. Since the clock at the point X was in motion, the runner A is moving faster than X, even faster than B. That means that A's clock should run slower than the clock at the point X and even slower than B's clock. In other words, time on B's clock runs faster than the clock at the point X and even faster than A's clock. These examples, in fact, explains how the measurement of flowing of time distinguishes depending on directions in which a body is traveling when measured by someone who's standing still. From the perspective of the observer I, when B is in motion toward the point X, space appears to be shrinking, and when A is in motion toward the point X, space appears to be expanding. According to the discovery of Edwin Hubble, everything in the universe is in motion at some speed in space due to the expansion of the universe. Therefore, the observer who is at rest in the above example is also subject to motion in the same direction in which the universe is expanding. In other words, I occupies the place of X. Correspondingly, the runner, who is running in the same direction as the train is identical to a person traveling in the same direction with respect to space expansion, therefore, time that runner or traveler experiences would slow down. On the other hand, the runner B who is running in the opposite direction is identical to the person traveling in the opposite direction to the space expanding direction, against the expansion. This consequence of space shrinks and speeds up of time. Also, the above experiment uncovers the mystery that why time flows only in the predetermined direction, toward future. As per the example, it is apparent that time flows in the direction in which the train is traveling. This is simple to understand by comparing the time that ticks on each clock at different points with reference to the observer's clock. This practical aspect of the experiment explores that, in space, the faster a body travels in the same direction in which space is expanding, the slower the rate of flowing of time will be experienced. Considering the facts of the result of the above experiment becomes unimaginably strange, as the runner B would reach the point X before the runner A, if both have started at the same time according to the observer I. However, in an expanding universe, two or more occurrences that take place at the same time in different locations cannot be regarded as simultaneity. That means, the further the distance between the locations, the more the time difference would be. As such, the runner A who is running in the same direction as the train, or an event that takes place closer to the point where space is expanding from, the point of the Big Bang, occurs before the other event that occurs at a distance from the aforesaid location. The events that occur in an expanding universe would occur in sequence with respect to the direction in which space is expanding. This is where the difference between the past and the future comes from. Therefore, the result of the experiment alters the question itself, as both A and B would reach the point X at the same time. However, A starts before B. This is not possible to experience in our normal life since the speed that we travel is very small. As speeds increase toward the speed of the expansion of the universe or the speed of light, the above-mentioned effects become more and more obvious. Perhaps the most unexpected result of the above experiment is the way in which our understanding of the nature of space-time has to be modified. When a body travels in space, the mass of the body and energy or force acts upon the body would curve space. That curvature of space would create shortcuts through which massless particles of the body can penetrate from one location to another, and through time. Conclusion. The conclusion of the concept is that whenever a body is traveling at a speed closer to the speed of light or the speed of the expansion of the universe in the same direction in which space is expanding, experiences a time that ticks slower than the time measured by someone who's traveling slower in the same direction or traveling in the opposite direction to the direction of space expansion, or being at the absolute rest. Any intelligent fool can make things bigger and more complex. It takes a touch of genius and a lot of courage to move in the opposite direction. Albert Einstein. Glossary and notes. The absolute rest is the point in space at which a body clustering the total mass and energy of the universe together would stand still against the expansion of space. In other words, the absolute rest is the point which the body traveling at the same speed as the expansion in the opposite direction to the direction of expansion would reach. The absolute fast, or the speed of the expansion of space, is the maximum speed that anything in the universe can travel. In the expanding universe, nothing with mass travels or can travel in the opposite direction to the direction of expansion. Everything, even that seems to travel in the opposite direction, still travels in the same direction as expansion. Since the result of this experiment is true and obeys the laws of physics, the idea of the expansion of the universe as assumed to take place in one direction is also true. I would like to present some great ideas in the future presentation, that could explain how space is expanding only in one direction, which is outward from the center point in three-dimensional space, despite the fact that it appears to be expanding in every direction, since galaxies are observed to be receding from one another in whichever the way it is observed. Thank you.